Hello and welcome. In this video, we're going to be sketching another type of function, going through every single step to successfully sketch the functions. I went through all these steps in detail in the playlist that's on the top right hand corner. Feel free to go and check it out. For today, let's say we have a function f of x equals x minus 4 over x squared minus 16. The first step to do is always to try and see, can I factorize this or no? And the answer is yes. Since the denominator is a difference of two squares, I can factor it. Why did I know that it's a difference of two squares? Because this number is a square number, means it can be square rooted. This number is a square number, it can be perfectly square rooted, and I have a difference sign in between them, so this makes a difference of two squares. So let's rewrite the numerator as it is, and the denominator can be written as x minus 4 into x plus 4. This is how I factorize a difference of two squares. I take the square root of the first number, the square root of the second number, I repeat it in both brackets, one bracket with a positive sign, one bracket with a negative sign, and that's it. So now, straight away, I can see that there is this factor, x minus 4, that could be cancelled with this x minus 4 over here. So I need to take care of this, because this is going to change my vertical asymptotes or holes, or as we are going to see. So first, let's start by doing the first step, which is finding the domain. The domain of the function is all the x values that are applicable, basically. So what x values here will make my function undefined? I know that anything over 0 is undefined. So I want to know what are my x values that will make my denominator 0. And these x values are the values that I cannot take in my domain. And straight away from here, I can see that if x is 4, this whole bracket is going to be 0, making everything undefined. And if x is minus 4, this whole bracket is going to be 0 as well, making everything undefined. If you want to go through like how to actually get it, you can set x minus 4 to 0. So you will get an x equals 4. And you can set the second bracket, x plus 4 equals 0. So your second x is going to be minus 4. So over here, your domain is basically everything except these two values. So x is not equal to 4 and x is not equal to minus 4. This is basically my domain. So all real numbers except these two numbers. So let's move on to the next step. Let's find the y and x intercepts. I always like to start with the y intercept. So the y intercept, meaning that I can set my x to 0. Over here, y is going to equal, instead of x, I'm going to put in 0 minus 4 over 0 squared minus 16. That is minus 4 over minus 16, which is going to give me a positive 1 over 4. So my y-intercept is basically the point 0 and 1 over 4. Now, for the x-intercept, I need to take care. Usually, for the x-intercept, I just set y equals 0. So let's do that for the factorized form. So let's say 0 equals x minus 4 over x minus 4 times x plus 4. So over here, if I multiplied both sides by 0, both sides by the denominator, okay, I can cancel this denominator and I'll have an x minus 4 equals 0. So you can tell me that, okay, the x-intercept or the root is going to be at x equals 4. That is wrong, because we factored or we cancelled a factor, then this doesn't work, because this point where it is x equals 4 is going to be a hole, or it's an x value that's undefined. And I can know that from my domain as well. So that's why I need to take care. So for x-intercepts, I will not have any x-intercepts. I will have none. X, if you told me x equals 4 is an x-intercept, I'll tell you that's wrong. So x-intercepts, none. Let's move to the third step. The third step is determining vertical asymptotes and holes. So again, vertical asymptotes and holes are values of x that will make the function undefined. And I can see here that I have two values of x that will make the function undefined. X equals 4 and x equals minus 4. The x equals 4 is associated with this factor, the x minus 4 factor, because when I set x minus 4 equals 0, I'm going to get x as 4. Or basically when I substitute 4 into this factor, it's going to make it 0. And in the other part, x minus 4 is associated with this factor, x plus 4. Okay, so I need to see x plus 4, did I cancel anything with it in the numerator? No, there is no shared factor with x plus 4 in the numerator, and I did not cancel. So this x plus 4, the value is going to become a normal vertical asymptote, nothing special over here. So x minus 4, which is associated with this factor, is basically a vertical asymptote. However, x equals 4, which is associated with this second factor, I cancelled it with the numerator. And I know when I cancel with the numerator and they're both the same degree, I get a whole. So this x equals 4 is now not a vertical asymptote. It's another type of an undefined x, which is a whole. This is very, very important to distinguish from. Okay, let's do the fourth step, which is determining the horizontal asymptote or the oblique asymptotes. So for again, horizontal asymptotes, I will divide everything here by the highest value of x, so highest degree of x, so it's x squared. So I'm going to divide everything by x squared, and I'm going to take the limit as x approaches infinity. And we went through every single step in details. Feel free to go check it out. So this is going to be x over x squared minus 4 over x squared over x squared divided by x squared minus 16 over x squared. So this is going to equal the limit as x approaches infinity of x over x squared is basically 1 over x squared minus 4, no, it's 1 over x minus 4 over x squared over x squared divided x squared is 1 minus 16 over x squared. When I take the limit as x approaching infinity, this is going to be 1 over a very large number, so it's approaching 0. This is going to be 4 over a very large number approaching 0. This is 1, and this is minus 16 over a very large number, so it's approaching 0. So basically 0 minus 0 over 1 minus 0 is basically 0 over 1 or 0. So my y, my horizontal asymptote is going to be at y equals 0. So let's erase this, and we know that now y equals 0 is a horizontal asymptote. Now, let's do part 5, okay? So over here, I can rewrite this as 1 over x plus 4, okay? And I know every other critical point. So what I can do is finding f dash of x, I can find f dash of x over here, let's say 5. F of x was equal to 1 over x plus 4. So let's try and find f dash of x. First of all, I can write this f of x as x plus 4 power negative 1. And I can use the chain rule to differentiate this. So this is going to be power times coefficient. So negative 1 times 1 is going to be minus 1 into x plus 4, and then reducing the power by 1, so minus 1, reducing that by 1 is going to be minus 2, and then multiply with the differentiation of what's inside the bracket. Differentiation of x plus 4 is basically 1. So our f dash of x is equal to negative 1 over x plus 4 squared. Now, let's try to find if there are any critical or stationary points. So over here, to find the critical points, I know that I need to equate my first derivative to 0. I need to equate my first derivative to 0 over here. So this is my first derivative. If I equated this to 0, will I get any value of x? No, because this bracket is always going to be positive. It's never going to be 0, and the numerator is never going to be 0. So no stationary points. So the next thing to do is to determine the intervals where the function is increasing or decreasing. To do that, we always draw our number line, and on the number line, we put the points where we have critical points. Critical points could be holes, vertical asymptotes, stationary points, or whatever. So over here we do not have any stationary points. However, we have a hole and we have a vertical asymptote. These are our critical points. So these are the points we're going to put on the line. So we have a -4 first, and then a 4. And then we will test a point to see the sign of f dash of x on every single interval in those 3 intervals in front of us. So let's start by taking an x value in this interval. This interval is basically from -infinity up to -4. I can take any x value. Let's take x is -5. So f dash of x is going to equal 1 over -5 plus 4 all squared. This is going to give me 1 over -5 plus 4. This is negative. So f dash of x is negative 1 over 5. So this is going to give me basically -1 as an answer. I don't care about the value. I only care about the sign. So over here, this is going to be having a negative sign, which means that at this part or at this interval, the function is decreasing because the first derivative has a negative sign. Over here, between -4 and 4, I can take simple x as x equals 0. F dash of x is going to be -1 over 0 plus 4 squared. 1 over 4 squared negative, so it's going to give me a negative value. So over here is decreasing. Since there are no stationary points, there are no points where the gradient changes its sign. So I would expect that everything will have the same, or f dash of x everywhere is going to have the same sign, because f dash of x changes the sign from negative to positive or vice versa only after a critical point or after a stationary point. Okay? So let's test a point over here. Let's say x equals 5. Again, 5 plus 4 is going to be 9. 9 squared. -1 over 9 squared is going to be basically negative value. So this is also decreasing. Now I finished part 5. Let's do the final part, which is getting f double dash of x, meaning that I will need to differentiate this once more. So let's write this as, let's write f dash of x first as negative x plus 4 power -2. And let's find f double dash of x. Power times coefficient, -2 times -1 is going to equal to 2 into x plus 4 power -3 times differentiation of what's inside, which is 1. So times 1, or I can just leave it like this. So this is equal to 2 over x plus 4 power 3. So over here, again, if I want to equate this to 0 to find any possible inflection points, I will not have any value of x that will make this 0. So no inflection points. So let's do the final step, which is doing the same number line and getting the intervals where the f double dash of x is positive or negative. And this helps me because when f double dash of x is positive, it's a concave up part of the graph. When it's negative, it's a concave down. So it's going to help me when sketching. So let's say x equals -4. X equals 4. Over here, let's take again x equals -5. F double dash of x is going to equal 2 over -5 plus 4 is -1. -1 power 3 is a minus value. So 2, which is positive, divide minus. So it's going to give me a negative value. So this part over here is a concave down part of the graph. Let's take x equals 0 here. So 0 plus 4 is 4. 4 power 3, that's positive. 2 divide a positive thing is going to be a positive value. So this is concave up. Again, if I took x equals 5 over here, x equals 5. 5 plus 4 is positive, power 3 positive. 2 over that is going to give me a positive value. So it's a concave up part of the graph. So now we are ready to sketch our function. So what we can do is we can get our graph and try to sketch using all the information we have. First, we always start by plotting any xy intercepts and the vertical and horizontal asymptotes. So our y-intercept was at x equals 0, y equals 1 over 4. Let's say that is around, so x is 0, let's say 1 over 4 is, let's say it's around here. So this is our y-intercept over here. Our y, or our vertical asymptotes, was at x equals minus 4. So let's say minus 1, 2, 3, 4. So over this line over here is basically a x, or a vertical asymptote over here. So this is a vertical asymptote, and we had a hole at x equals minus 4. So no, at x equals 4. So 1, 2, 3, 4. We have a hole over here, so we know that we're going to continue the function normally, and then when we reach x equals 4, we're just going to put a hollow circle. Okay, we know that we have a horizontal asymptote, which is this part at y equals 0, which is basically the x-axis. So I can do this. This is a horizontal asymptote over here. Now, I know that from this number line, I will have a decreasing function before, so this is minus 4. So before minus 4, I'll have a decreasing function. I have two options in a rational function, either to draw it like this or like this. Which part do you think is going to be the decreasing? Which part is going to obey this decreasing part? Is it 1 or 2? It's 2. Yes, and also if I see that it's a concave down function in this interval, so it must look something like this, okay? And then after minus 4 up to 4, I also have a decreasing function. I can have two options to draw this with my vertical and horizontal asymptotes. I can either draw it like this, or I can draw it like this. However, it's already given away from the y-intercept that's going to be on the upper side of the horizontal asymptote, and this also goes with the f dash of x is going to be a decreasing function, as I can see that the gradient is negative, and it's going to be a concave up part, so it needs to look like this, so it will look like this part over here. So let's sketch this part, knowing that when x is equal to 4, I will have a hole over here, so I can come here, erase a little bit, and just put a hole at x equals 1, 2, 3, 4. So this is a hole. This is how to sketch my function. Sketching functions, sometimes you don't need to do all the steps. Like if you do the steps up to this point, I think it's enough for most questions. However, for more complex questions, including inflection points, you will need to do part 6. And by the way, this series is to how to properly sketch every single function from A to Z, not missing anything, not missing an inflection point, not missing a hole, not missing a vertical asymptote, not missing anything, not missing even an oblique asymptote. So that's why it's a little bit longer. However, it's very important to understand how to do every single step for future. Anyways, thank you for watching. I hope this video was helpful. Leave a like, comment down below, subscribe, and yeah, have a nice day.